Good morning, everybody. Can you hear me? Fantastic. Thank you so much for the organizers. Thank you, Annie, and everybody for being here. I am Pablo Giuliani. I'm something special at EFRIT. My position is hard to describe, but I work on research for EFRIT-related questions and mostly on graduate student success. I'm helping graduate students at the lab to thrive, and I see many of my friends, grad students here in the audience. And I'm extremely happy to be able to open the talks today. My talk, let me hide this. Okay. My talk is called Stars, Nuclei, and Goats in Theory, because I didn't know what to give the title of my talk. So I hope you enjoy it. This is the menu for today. These slides are going to be available for everybody, and this QR code is going to appear repeatedly, so you can take a picture whenever you see something interesting. This is a menu for today. I'm going to talk a little bit about my journey because I want to show that we can change paths, and that is completely fine. Then I'm going to dive into Bayesian statistics and machine learning for nuclei and stars. We're going to talk a little bit about dimensionality reduction because that's one of the main research areas that I'm involved in. And then we're going to close with a couple of takeaways. A disclaimer on the topics. This presentation has 112 slides. You're not expected to grab everything from it. I want to use it as a resource so that you can come after if there was something that you like and you can take a look and it will help you, I hope, in your research and other things. A disclaimer on the content. This is done with a huge team of people, especially with those 3 dots over there that I'm missing a lot of my friends and colleagues that have made all of this possible. This is not, it's not even me. I'm just lucky enough to have all these friends that do amazing work. Okay, so a little bit about my journey. That is me with my dog, Dirac. I try to put him in every slide, every presentation that I give. I did my undergrad in Caracas, Venezuela. That's where I am from originally. I moved to Florida State University to do a PhD. I searched somebody that was the nicest person in the department. That person, Jorge Pikarovich, ended up doing nuclear astrophysics, and that's why I am here today. Then I went to Michigan State to do a postdoc, and I stayed there for the position that I described. So this is how my university looked like. That is how Florida State looked like. And I'm now in Michigan in the middle of the snow, and I love it. I'm actually very happy, but it was a drastic change. The changing path that I wanted to say is that whenever I was in undergrad, I was doing experimental physics in analyzing pattern formation in sand, in vibrated sand. And then I went to Florida State and I say I want to do nuclear theory with Bayesian statistics and machine learning, and everything worked out fine. So if you're sitting in your chair and you're thinking, nuclear astrophysics seems boring, I want to do something else, that's completely fine. I want to say that's completely fine as well. There are many different paths, and we don't have to follow the exact same one to be successful. Now, as I mentioned, I am at EFRIT. I see EFRIT as that boat over there. I asked ChatGPT for help to make that happen. And I see it as this incredible thing that we built to be able to explore the landscape of things that nobody has ever seen before. And in there, I'm not only involved in all of these things. You see the first goat in the Bayesian statistics part, but I'm also involved in education, outreach, and community. Some of the big questions that we try to address in there relate to the different areas of the logo that are showing in the EFRIT logo. Things about structure, astrophysics, applications, symmetries. And in particular, important for this conference is the astrophysics part, and where, a cool question to ask is, where did the elements come from? I will touch on that a little bit later. But the important thing that I want to highlight is that we do all that having fun. And the lab has a very good community environment in where we have ice cream every time that we discover a new isotope, or every second Thursday, whichever comes first. We engage with the public. We have luncheons every Fridays. We have a filmmaker that is making a documentary about the lab. And I was going to show the teaser, but I think I already have too many slides. So if you're interested, please reach out to me and I will be more than happy to share that with you. We also have a piano, and that's why I needed the sound. We go for the piano every day with a group of friends. This is me and one of the grad students in there improvising together. So the point that I want to make is that basically we have a blast while we're trying to tackle these big questions. Okay, let me go to the Bayesian statistics and machine learning part. And I think I'm doing fine on time. So I want to motivate why we will want to do machine learning and statistics for the questions that we have now in nuclear physics. So for that, Let me start with the Monty Hall problem. By show of hands, how many of you have heard of this problem before? Okay, I see many, many hands. For those that haven't, so those that have heard, don't say anything yet. For those that haven't, I want you to think about this problem. Imagine that you're in a show, TV show, and the host tells you, behind one of these 3 doors, there is a golden ticket for a sure NSF proposal. You get that ticket and you get a proposal without any review. You can do whatever you want for it. Behind 2 of the doors, there is goats. So you want that ticket. So you choose 1 door at random, and then the host tells you, well, there is a goat. Let me show you that behind door 3, there is a goat. Now the question is, should you change doors or stick with your guts and think that in door number 1, there is the NSF ticket? You have 10 seconds to think about this. So by show of hands, how many of you will stay, those that haven't heard about the problem, how many of you will stay in your current door? Okay, I see a few hands. How many of you will change? Okay, I see a few hands. Turns out that if you change, you end up having twice the amount of chance of getting that NSF golden ticket. And there is reasons for that. We can discuss in detail later. But what I want to illustrate is how just doing a little bit of statistics will get you twice the amount of chances, in this case, of resources, information, however you want to call it. And that's why I want to highlight that this is an important part of the scientific process. By the way, for those of you that have heard about the problem, extra question, what happens if the host didn't know where the goats and the golden ticket was? They just choose a door at random. Will that change the outcome? Think about it. Machine learning, about how to apply machine learning for our problems. Here is our classic example, and I want you to think without explicitly using any TensorFlow and any neural network. If you were, I don't know, 50 years ago, how would you write a Python code that classifies the numbers, just out of scratch? Think about it. You have 10 seconds. Let me show you how we'll do it. I go and talk with ChatGPT, and I say, ChatGPT, can you help me write a code to classify, download the MINTS dataset and classify them and show me the performance? And the thing just did it, and it did a fantastic job. And at the same time, I asked it, can you make a picture, a drawing of a robot classifying the numbers? And it was able to. So I'm not saying we need to do science using ChatGPT, but clearly there's a lot of tools out there that are extremely useful and that they were not available decades ago, and we better tap into that. Let me talk about the challenge and why these things require such approaches. We're trying to do nuclear astrophysics, and it's an extremely complex field. The way that I like to explain this and why I see that this is very complex is because of 2 main reasons. The first one is that the rules are unclear. It's as if you're trying to watch people playing chess and trying to come up with the rules of chess just by looking at what they do. But you can only watch from very far away, and it's very dark. And half of the screen doesn't work because whenever you do experiments with neutrons, it's really hard to detect them. So most of the time, you're just seeing what the protons do. And you're wearing sunglasses. And out of all of these, you're trying to figure out what is happening. And the main issue also is that you can only watch one instant at a time every time that your friends at the lab make an experiment or your astrophysics friends point the telescope. So that is the first challenge, the first thing that makes this very challenging. The second one is that even if you have the rules of the game figured out, there is this thing called the emergence of complexity. And in that one, very simple rules, like the game of life, that you figure them out precisely, can give rise to extremely complex phenomena that no way you were going to be able to predict this out of just the starting simpler rules. So this is the reason why you need a very healthy theory experiment observation cycle. And my point is that at the heart of that, in this day and age, we want to use statistics and machine learning. Let me show that in a specific example related to this conference. At FRIP, I mentioned we have all these things that we're interested in. Let me pick astrophysics. I want to understand the R process. For that, I need a lot of data and a lot of predictions from models. Lifetimes, masses, capture rates. By the way, there is going to be many talks about this, but in particular, I want to highlight the talk of Ante on Wednesday, who's going to be talking about capture rates and how to calculate them from nuclear theory. Let's focus on masses. Suppose that you want to use many modes to calculate the masses. You have all of these, and as soon as you start playing with varying the different modes that you can get, you start getting different outcomes from the abundance pattern. So then you say, cool, let's make experiments so we can constrain our models better. There's many experiments that you can make, and all of those experiments in many different nuclei in the chart. And on top of that, if you want to connect with the the observations of stellar environments, neutron stars, and radii and mergers, yeah, it gets really complicated if you try to optimize all of this. Okay, so I think I have convinced you that this is important. There is a lot of resources online. We put together a summer school last year in where we guide people on the first early stages of doing statistics and machine learning. If you're interested, I will be more than happy to share those with you. As a quick overview, because I know that you're going to be seeing these type of equations in the rest of the talks, how does Bayesian statistics works in 3 minutes. That is probably a picture of probably not Thomas Bayes, but people usually put it and call him Thomas Bayes. So you're going to see these equations and plots like the ones that I have on the left. You have a prediction, you want to have uncertainty bands with your predictions, and then you want to have posterior distributions of your parameters or the quantities that you're interested in. The way that the Bayes equation works is that the thing that you want, which is the posterior of the distribution of the parameters given the data, we usually write it as a composition of 3 terms. The first one, that is likelihood, is what we think happened for a given set of parameters, the prior ideas that we have about our model, and the evidence, which usually we regard as a normalization constant, but it actually tells you how much all of the things that you're doing make sense. This has 2 clear advantages, in my opinion. The first one is that you are making clear assumptions about how all of these things interact with each other, so that somebody can come and say, actually, I don't believe in this thing that you did it. I think we need to use heavier tails for your errors. And the second one is that it allows for this natural refinement of knowledge. Whatever was the posterior of today is going to become the prior of tomorrow. Let's go over a quick example on how these things will work in paper. Suppose that I have my data, that are the blue points, and I'm trying to fit, I don't know, a linear model to it. So my linear model has 2 parameters. Let me see, I have a laser. Nope. Has 2 parameters, the intercept and the slope of the line. So my prior could be, well, I know that these 2 things should be around, I don't know, between 0 and 2 for the intercept and the slope. So you can put a Gaussian prior on that. And here just some code to help you, guide you through that if you want to try it. The likelihood, in this case, you can say, well, what I think is happening. I think that I have a central model, which is my purple line. And in there, the data in the red point is my observation J. And that I think is distributed along this line, but something happens, some random noise that I don't have control over that I'm going to model as a Gaussian noise, fluctuate at that point from the straight line downwards in this particular case. You can imagine that this is basically a Gaussian distribution that is centered in there if you think that your errors are Gaussians. And whenever you start writing your likelihood, you will say, well, each one of my points is distributed according to this Gaussian probability. If you combine them all, if you say that they're independent, eventually you arrive at the expression that many people use, which is e to the chi-square. And you're trying to do a chi-square fit. This has an underlying statistical assumption that many folks, me included before I play with all of these things, don't have readily available in their heads. And this could cause problems because if your errors are not independent or if they don't follow Gaussian distributions, you don't know exactly where to change what in order to create a better likelihood model. But now you do. So now you can play with these things. At the end of the day, once you have defined your likelihood and your prior, you want to calculate your posteriors. Usually this is done by Monte Carlo sampling techniques, which can be very expensive, and we're going to talk about that in a second. But after you sample this thing 100,000 times, you end up obtaining posterior distributions that I'm going to say they look like a long list of your visited parameters. And from there, you can actually predict new things. And you can create your uncertainty bands on the prediction of your models by sample on those parameters that you got. That's basically how it works in a nutshell in 3 minutes. So high five, we were able to make the goats proud. Okay, let me go to the dimensionality reduction part, which is another part that I want to talk about. Let me talk about one of my favorite topics lately, which is called model order reduction. So remember the thing that we said, you have your central curve, you're trying to make the goat sprout, so you want that uncertainty bound around it. By the way, I don't think I mentioned this. The reason why I associate goats with statistics is because when I moved to Michigan State, one of my mentors and advisors, he is a farmer, and as a hobby, he does statistics. So I went to his farm every Friday to talk about statistics and herd the goats and the sheep that he has. That's why for me, those 2 things are linked. I think it was important for me to explain that. Anyways, so we're trying to make the goats and Frederick, my mentor, proud. So we want to write this posterior distribution. The problem is that many times you might have to sample these things thousands, even millions of times to actually get an uncertainty band that makes sense. If each one of your evaluations takes a second, that will take you 2 months. And if each evaluation takes an hour, that will take you half a century. And there are evaluations that take an hour or more. For example, if I want to use time-dependent density functional theory to model collisions, that takes many, many hours. If I'm trying to calculate potential energy surfaces for fission, and that is important for example, recycling, fission recycling in the R process, that will take a very long time as well. So we want to create emulators, surrogate models, reduced order models, however you want to call them. I like to think of the analogy of, I cannot believe this is not butter. So we have the butter, that is a full evaluation of your model or your posterior. And I want to replace that by something that's still, tastes like butter, that doesn't have the problematic part. In that case, I guess lactose intolerant people will be very grateful. In my case, I want to finish these calculations within my lifetime. There are many things that you can use to build these. I cannot believe it's not butter. I'm putting this. You see that all of those things have links. So if you have the slides later, you can click on any of those if you're particularly interested. So how does it work for reducing the calculation, your model to make it go faster? There is an hour in YouTube of me talking about that. So I'm going to talk again only for 3 minutes. But if you're interested, you can watch that video. I have my friend Galerkin shooting lasers out of his eyes. So it's a fun presentation to watch. It works in 2 steps. You need to find good reduced coordinates, and you need to find good reduced equations for those coordinates. As an example, imagine you have a brick, and if you want to understand how the bricks move in space, somebody might tell you you need to calculate the trajectories of each one of the 10 to the 24 atoms. You say, no, I'm a physicist. I know I don't have to do that. I probably can get away with 6 degrees of freedom, 3 translations, and 3 rotations. For the equations for those things, you write your Euler-Lagrange equations or Newton's equations, F is equal to ma, and the torque equivalent one, and you're done. You don't have to calculate 10 to the 24 equations. Now, the problem is that for many calculations, it's not as obvious where the redundancy is coming from. And there are many techniques that people have developed to help you to find these redundant things and create your reduced coordinates. In this example, I'm showing one that is called the reduced basis method, in where you say, I'm going to expand my functions that I'm trying to solve from differential equations in a set of reduced bases where my reduced coordinates are the amplitudes of these things. And I obtain them. Principal component analysis is actually very easy to do. Then to find equations, you use something that is called the Galerkin projection, that is Galerkin with big classes. And if you want to know about this more, please talk with me afterwards. It's a fascinating topic. In an animation, the way that it looks is that now you have, for example, the harmonic oscillator. You're changing one of the parameters, is moving up and down, and instead of tracking what is happening to the wave function at each location as you change the parameter, you just track 2 numbers, A1 and A2, which are the 2 coefficients that tells you how the reduced basis is evolving. Now, you can visit the PCA doctor, and she will tell you if your problem is amenable to this linear embedding, which is what we call this particular dimensionality reduction technique, and that can tell you before you spend hours and days if this is something that you should try. We have created a lot of resources to help you if this is something that you would like to achieve. I'm highlighting one of them, which is a Jupyter online book with a lot of friends. I'm citing all the collaborators. Megan Campbell, by the way, is a high school student at St. Louis, Missouri, and she's having a blast with us, and I'm very happy. I'm going to talk about the importance of lowering the barrier later in the talk. The next person could be you. So if you're interested in contributing to these things, again, contact me. I will be more than happy to help. This is just to show off that we have been able to apply this to a lot of problems. And in almost all of the problems, we get speedups between 100 times faster to 10 million times faster than the original calculation. So this is the thing that actually enables you to really do uncertainty quantification. I want to highlight 2 that are going to be talks for later today by Rahul and Brendan. And they're going to talk about applications of these for the TOV equations and for quantum Monte Carlo. I always get that. Okay, I got that right. Okay, let me go, and I'm doing perfectly in time. I have 6 more minutes, and we're going to finish it. Let me talk about the second dimensionality reduction approach, and I'm very excited. It has to do with model combination. Remember when I had these slides, and I was saying, so what are you going to choose if you need to create your mass table for your R process calculation? It will be nice if you could combine the models in some way. I don't know if you know, but a group of ravens is called a murder, and a group of goats is called a herd. A group of models, I'm going to coin the term, I want to call them a congress of models. We'd like to have a congress in where every model has some sort of vote instead of having a selection of just one. So there are many techniques that you can use to actually do this in a Bayesian way. And this week, 2 people are going to be talking about some of these applications of Bayesian mode mixing and Bayesian mode averaging, targeted specifically for nuclear astrophysics. So the one that I want to talk about is this recent paper that I wrote with 3 friends and collaborators. I want you to think that whenever you're predicting the nuclear binding energies of nuclei, this prediction is actually a very long vector. I don't know, 2,500 dimensional vector. It's an arrow that is pointing in this high dimensional space. And if you have many models, what you have is many arrows. And what could happen is that some of them end up being collinear. They are not really contributing a new direction. It's just the same model fitted to maybe slightly different data. So if you were to write a combined model as a linear superposition of these models, you might run into trouble because some of them are going to be contributing the exact same thing. You visit the PCA doctor and she tells you, yes, you have many arrows that are redundant. The singular values are decaying exponentially. That means that we can reduce the dimension of this thing. So for that, what we did is just a principal component analysis on the group of models, and then we're combining the final model F as a linear superposition of these principal components. And the thing works, in at least the examples that we try, like a charm. It allows you to find collinearities between actual nuclear mass models, and it allows you to build these Bayesian posterior distributions to have very good uncertainty bands on predicting, in this case, the binding energy of tin for the different isotopes of tin. More importantly, what we have seen is that it seems to be very good at extrapolation, which is something very important because you're going to want to use these covariance tables of masses that you build from your combination of models to be able to predict things for the process path, for example. That way, we also make the goats very proud. Okie dokie, where are my takeaways? And I have 4 more minutes, so I don't have to rush. I'm very happy. Thank you for bearing with me until now. So for takeaways, I have 2. My first takeaway is that these methods in statistics and machine learning are propelling nuclear astrophysics towards a new era of discovery. And I hope that I was able to give you at least a couple of examples that excites you. Now you want to read all about it and how to apply it. My second key takeaway, and this is the most important, at least for me, is that these are things that can help us lower the barrier for more people to contribute to the scientific discovery process. Let me deviate from my conclusion slide for a second to give the detail. The way that I see these things, statistics and machine learning, it's called statistics, data science, because it's basically the same. It has 3 nice properties. The first one is that it's widely applicable and highly transferable. That means that if you train somebody on these things, they can go and do something else that it's not necessarily the same problem that they were focusing on, including going to different fields beyond academia, for example, like industry. It's something that is almost self-trainable, and that's something that we have observed whenever we're working with the high schoolers and the undergrads. There's so many guides and so many people are so excited about these things that you can just point out, read this book, take a look at these videos, and let's try to apply whatever you learn to my actual scientific science problem, and seems to be working very well. And the third one is that it's exponentially impactful. This is, curious enough, a paper on how machine learning, and they use machine learning to do this, how machine learning is growing exponentially in its impact to scientific papers. So I believe, together with many other people, that this is a perfect opportunity to create a more inclusive environment for science. And given that in the long-range plan, that is one of the things that we said is very important, that we need to draw talent from all across the US, this is a good way to do it. And I want to highlight the talk by Shelley Lesher. She will be talking, I think, around 11:30. Here she is in the DMP in October of 2022 with all the undergrads that she was able to coordinate to have the experience of coming to the talk. So in that effort, me and my friend Kyle have created this forum and this network in where people can come in contact with each other and collaborate and share resources. In particular, I'm using that for a course that I'm going to be giving this summer on coming up to speed, many important things that maybe you didn't see in your undergrad and you may need for your grad school. So if there is anybody here that is starting grad school or is interested in attending in any way, we start on Wednesday. Let me know and I will be more than happy to provide the Zoom. The final thing that I'm going to say, we have this pilot program with Pink, with Paul Gay. If you haven't met Paul, I recommend that at some point you get a hold of him, fantastic person. And what we're doing with this is showing a bunch of high schoolers these tools and how to apply them for actual research. And we're writing a paper with a group of them. I'm so excited. I'm going to have a paper with a bunch of high schoolers on dimensionality reduction techniques. So my second takeaway now coming back is that these things are not only propelling in the area of discovery, it's the type of things that I think will be able to enable us to move forward in the inclusion. With that, I would like to thank the people that have paid for my lunch for the past years. I like to thank the organizers, especially CB and all the friends that brought me here. I want to thank all my friends and collaborators, which is a very long list, and I leave these resources for you if you're interested in more things. Thank you very much.